Okay, private message me your answer once you're done. All right, so the answer is the convenient number 1, 2, 3, and base 6. We can check this by just converting the base 10, like the following. 36 plus 12 plus 3, right? Yeah, that's easily verifiable as 51. And okay, since we didn't get it on the recording earlier, which is the main, and this the main subject, which at the AMC level you might not have heard before, I'll just go over and reiterate what bases are and how they work. So we count in base 10 where the place values represent powers of 10. Then the digits represent what multiple of that power of 10. For example, a number like 809 would represent 8 times 10 squared plus 0 times 10 to the 1 plus 9 times 10 to the 0, where these digits, as I said, they indicate what multiple of each power of 10 there are. And if this were something greater than 10, why isn't this not allowed? Because then this could just be 10 plus 1 times 10 squared, and it could go to 1 times 10 cubed plus 10 squared. So this is, and then when we rewrite this, this will just be 1109, right? So this is why we restrict numbers, valid digits in that base, in its base, to be less than it. Okay, so and analogous to base 10, other numbers work the same, just in different place values. Like you can have 234 in base 8, and this is the 64th place, the 8th place, and the 1's place, since those are the powers of 8. And our values, the value of this number in base 10 is what we can just quickly evaluate by expanding this value. And bases are often intimately tied to mods in number theory, as well as other concepts, since they really revolve around divisibilities and also exponents of and multiples of a certain number. So anyways, let's calculate this quickly. So this is 128, right? Plus 24 plus 4, 156 should be our answer. Okay. And to convert from base 10 to another base, which is usually what you'll be doing, but not always, you will have something like 51 in base 6, which is what we just did, or 51 to base 6, which is what we just did. So first we do 51 divided by 6 squared. Q quotient is 1. Remainder is equal to 15. So basically this sees the coefficient of 6 squared. And we always pick the biggest power that is small, less than or equal to the number in question to make sure we get the right digit. And 15, we've divided 15 by 6 to the 1. Quotient is 2. And then 3 times 6 is 0 is left. So it would be 1, 2, 3 base 6, as you can see. 1 times 6 squared plus 2 times 6 to the 1 plus 3 times 6 to the 0. All right, so that should be fairly straightforward. So we were talking earlier about like notation and like what valid digits would there be for numbers that are like, I don't know, more than 10, right? There's notation for representing numbers in different bases. We use a subscript with the basis value, as you've been seeing me doing. Like how the exponent is this small number up here. Base would be this small number down here, denoting like what base it's in. And so instead, so when we overflow and we get valid base digits that are more than 10, what we simply do is we just start to use letters. So 10 is A, if we had like base 11, and then 11 would be B, and etc. And now this is very important since computers use powers of 2 binary to do their work. So we would want to use like some power of 2, and notably 16. And this is notable since like A, B, C, D, E, F are valid digits in base 16. Well, this represents 10, this 11, this 12, this 13, this 14, and this 15. And so I will give you some examples using this like notation digits. And well, hexadecimal is actually very easy to like store base 2 numbers since like if you think about it, base